For the next 10 minutes, picture an object so extreme that if you stood anywhere near it, it would rip the iron straight out of your blood. Imagine a magnetic field so intense that it bends atoms, twists space, and crushes matter into bizarre shapes. Before we go deeper, make sure you watch this video all the way through. The journey we're about to take is full of twists, extreme physics, and mind-bending cosmic phenomena. Missing even one part would be like skipping the climax of a movie. So settle in, because we're about to explore the terrifying beauty of magnetars, the strongest magnets known to exist, and the forces that make them so unbelievably powerful. Let's begin with something familiar. Magnets. You know how they work. They attract metals, they stick to your fridge, they power electric motors. But even the strongest magnets humans have ever built massive superconducting coils. Cooled to near absolute zero R. Nothing compared to what nature can create. The strongest human-made magnets reach around 100 Tesla. That's impressive. But a magnetar? A magnetar reaches 1 quadrillion Tesla. That's a 1 followed by 15 zeros. It's a magnetic field so intense that it defies intuition. It's the kind of magnetic field that doesn't just pull on metal, it distorts atoms, crushes electrons, and twists the very structure of matter. So what exactly is a magnetar? A magnetar is a type of neutron star, the collapsed core left behind after a massive star explodes in a supernova. When a star, much larger than our Sun, reaches the end of its life, it runs out of fuel, collapses under its own gravity, and then explodes outward in a violent burst of energy. What remains is a neutron star, a city-sized object with more mass than the Sun, packed so tightly that atoms are crushed and electrons merge with protons to form neutrons. A neutron star is already one of the most extreme objects in the universe. But a magnetar is even more extreme. It's a neutron star with a magnetic field so powerful that it becomes the strongest magnet in existence. To understand how strong a magnetar is, imagine this. If you placed a magnetar halfway between Earth and the Moon, its magnetic field would wipe every hard drive, every credit card, every electronic device on Earth. If you stood within 1,000 kilometers of one, your atoms would literally be torn apart. The magnetic field would stretch your body into a long, thin line of plasma. Magnetars are not just dangerous, they are cosmic nightmares. But how does a magnetar get such an insane magnetic field? The answer lies in the physics of collapse. When a massive star collapses, its core shrinks dramatically. And when something shrinks, its magnetic field intensifies. It's the same principle as spinning a figure skater. When they pull their arms in, they spin faster. When a star collapses from the size of a planet to the size of a city, its magnetic field skyrockets. But magnetars go even further. They are born from stars that had unusually strong magnetic fields to begin with. And during collapse, those fields are amplified to unimaginable levels. Now let's talk about what magnetars actually do. Their magnetic fields are so intense that they cause the surface of the star to crack and shift. These cracks release enormous bursts of energy called starquakes. A starquake on a magnetar can release more energy in a fraction of a second than the Sun emits in 100,000 years. In 2004, a magnetar called SGR 180620 released a burst so powerful that it briefly altered Earth's ionosphere from 50,000 light-years away. Think about that. A starquake on a magnetar halfway across the galaxy affected Earth. That's how powerful these objects are. Magnetars also emit strange bursts of X-rays and gamma rays. These bursts can be so intense that they saturate detectors on satellites. Astronomers sometimes detect magnetar flares by accident because they overwhelm instruments designed to study much weaker sources. Magnetars are unpredictable, violent, and incredibly dangerous. They are cosmic ticking bombs. We're about halfway through the video now. So if you're enjoying this deep dive into the universe's most extreme magnet, make sure to like the video, subscribe to the channel, and turn on the notification bell so you don't miss any future explorations. Your support helps this channel grow and lets me keep making videos like this one. Now let's explore what magnetars look like. A magnetar is small, only about 20 kilometers across. You could fit one comfortably inside a major city. But despite their tiny size, they weigh more than the Sun. Imagine compressing the mass of a star into something the size of a town. The density is so extreme that a single teaspoon of magnetar material would weigh billions of tons. The surface of a magnetar is a crust of superdense matter, and beneath that crust lies a sea of neutrons packed so tightly that they behave like a single quantum object. The magnetic field of a magnetar is so strong that it shapes everything around it. Light itself bends in strange ways. Atoms stretch into long, thin shapes. Chemistry breaks down. The rules of physics that apply on Earth simply don't work near a magnetar. Even empty space behaves differently. The vacuum around a magnetar becomes polarized, meaning it acts like a lens that bends light. This effect is predicted by quantum electrodynamics, and magnetars are one of the few places in the universe where such extreme physics can be observed. Magnetars also spin. When they're born, they can rotate dozens of times per second. Over time, their magnetic fields slow them down, but even then, they remain incredibly fast. As they spin, their magnetic fields sweep through space, generating powerful electromagnetic waves. These waves can accelerate particles to near light speed, creating beams of radiation that shoot out into the cosmos. Sometimes these beams sweep past Earth, and when they do, we detect them as bursts of X-rays or gamma rays. Let's talk about how magnetars affect their surroundings. A magnetar sitting inside a cloud of gas can heat that gas to millions of degrees. It can strip electrons from atoms, creating glowing regions of plasma. It can disrupt nearby stars, distort their magnetic fields, and even trigger star formation by compressing gas clouds. Magnetars are not just passive objects, they actively shape their environment. But magnetars don't last forever. Over tens of thousands of years, their magnetic fields weaken. They gradually become ordinary neutron stars. Their violent flares stop, their starquakes fade, and they settle into a quieter existence. But even then, they remain incredibly dense and powerful. A magnetar's legacy can last for millions of years as the shock waves from its flares ripple through space. Now let's explore something even more fascinating. Magnetars might be connected to some of the most mysterious signals in the universe. Fast radio bursts, or FRBs, are incredibly powerful flashes of radio waves that last only milliseconds. For years, scientists didn't know what caused them. But in 2020, a magnetar in our own galaxy produced a burst that looked exactly like an FRB. This was the first direct evidence that magnetars might be responsible for at least some of these mysterious signals. It means that magnetars are not just powerful magnets, they might be cosmic radio transmitters, sending out bursts of energy that can be detected across billions of light years. Magnetars may also play a role in gamma-ray bursts, the most powerful explosions in the universe. Some gamma-ray bursts are thought to be caused by the birth of When a massive star collapses, the newborn magnetar can release enormous amounts of energy, creating a burst of gamma rays that can be seen across the cosmos. These bursts are so powerful that they can briefly outshine entire galaxies. Let's shift to something more philosophical. Magnetars remind us that the universe is full of extremes. They are objects that push physics to its limits, places where matter behaves in ways we can barely understand. They show us that the universe is not just beautiful, it's terrifying, violent, and full of unimaginable forces. And yet magnetars also help us understand fundamental physics. They allow scientists to test theories about quantum mechanics, relativity, and the behavior of matter under extreme conditions. In a way, magnetars are laboratories for the universe. Now, let's talk about some famous magnetars. One of the most well-known is SGR 180620, the magnetar that produced the massive flare in 2004. Another is 1E 1048.15937, a magnetar known for its unpredictable bursts. There's also XTEJ 1810197, a magnetar that suddenly turned on as a radio source in 2003, surprising astronomers. These magnetars are scattered across the galaxy, each one a tiny but incredibly powerful beacon of magnetic energy. We're getting close to the end of the video now, and I want to take a moment to reflect on what we've learned. Magnetars are the most powerful magnets in the universe. They are born from the collapse of massive stars, and their magnetic fields are so intense that they distort matter, bend light, and reshape space. They produce violent flares, starquakes, and bursts of radiation that can be detected across the galaxy. They may be responsible for fast radio bursts and some gamma-ray bursts. They are cosmic monsters, but they are also cosmic teachers, helping us understand the laws of physics at their most extreme. Before we wrap up, I want to ask you something. What surprised you the most about magnets? Was it their magnetic strength, their violent flares, their ability to distort matter, or the fact that they can affect Earth from tens of thousands of light years away? Let me know in the comments, because I love hearing your thoughts and seeing what part of the universe captures your imagination the most. And as we reach the end of this cosmic journey, don't forget to like the video, subscribe to the channel, and turn on the notification bell so you never miss a new exploration. The universe is full of mysteries, and together we can uncover them one by one. Thank you for watching, and until next time, keep looking up.